see at the top where it says limits of sequences of numbers. So what this chapter really gets into is infinite sequences, infinite series. We are starting with the idea of a sequence. So an infinite sequence is a set of numbers whose domain is a set of integers. So that's important. When we start talking sequences, sequences are going to be integers that are greater than or equal to some initial integer, whatever we define that to be. You're going to be given what's called an nth term. That's really just your general term. So it's kind of like your function. You dealt with sequences a little bit when you did Math 1, but that might have been a number of years ago now, obviously. That's your initial term, and that's how you're going to get each subsequent integer from that term. We've already talked a little bit about convergence and divergence when we did improper integrals. It means the same thing here. If we converge, what that tells us is that sequences of numbers is going to approach a limiting value. And if that's the case, we're going to say it converges. If that sequence does not approach a single finite number, then we're going to say that that sequence of numbers is going to diverge. All right. So the way we're going to experiment or show this, and I think hopefully makes some sense as you see these, is with a little graph. So this says graph the following sequences to determine if they converge or diverge for this idea. As we go to infinity, what's going to happen? Do we approach a limiting value and converge, or do we not, and then would say that it diverges? So what we're going to do is sketch in this one. We should just need kind of a first quadrant here. And then it's really just a little x, y plane. So these will be our n's. These will be our a sub n. So really just x, y's. We're just making it fancier than probably what it needs to be. So let the first one be a 1. 1 minus 1 is going to be a 0. So that's our initial one for this one. If I plug in a 2, I'm going to pop up to a 1. If n is a 3, I'm going to be at 2. If n is a 4, we're going to be at 3. And if we now think graphically how this plays out, and we start thinking about the idea of converging upon a certain value or diverging, when we look at this, does this appear as if this is going to converge upon a limiting value? Is there a ceiling there? No. All right. So when that happens, we would say that this diverges. Our number is just going to get bigger and bigger and bigger and bigger. Similar with number 2, yeah, you're only going to need a first quadrant. However, when you draw in the first quadrant, we're going to change our window by hand here. So go ahead and do 1, 2, 3, 4, 5, however many we want to try to get to at least 4, probably. We have 5. And then just make the very top one a 1. All right, then plug in. Let n be a 1. So you would get 1 over 1, which is 1. So we're going to be way up here. If you let your n be a 2, then you're going to be at 1/2. So that's halfway in between then. If you let your n be a 3, we get 1 over 3. So that's 1/3 of the way up. If we let n be a 4, we would get 1/4. So that's 1/4 of the way up, a little smaller than that one. And then 1/5 should be 0.2, kind of looks like this. We could jump to 100. If I did 1/100th, wouldn't that be really, really close then to the x-axis? So if we were to continue this, and we don't really want to connect these, remember these are sequences, they're integers only, these guys here, so we don't want the stuff in between. It's the whole discrete continuous stuff that you would have done in those wonderful Honors Math 1 days. So this is a discrete idea. Does this appear to be approaching a limiting value? Yeah. So we would say that this one converges, and it's converging to, what would that limiting value be? 0. So we would say that that sequence converges to 0. All right, so the next one, same thing, first quadrant only here. We'll go to 5, I think, should be good. Yeah, and then same thing, just put a 1 at the very tippy-toppy there. Throw in the 1, you're going to actually start at 0. If I throw in a 1, understand now how, I'm sorry, I marked that wrong. When n is a 1, we get a y value of 0. So that should be right here. And then if I throw in a 2, I would end up with a 1 on top and a 2 on the bottom, 2 minus 1 over 2. So that's halfway up. If I throw in a 3, I would then get 2 on top, 3 on the bottom. So that's 2/3 of the way. If I throw in a 4, I would then get 3 over 4, a little higher up, and then 1 more. If I do 5, I would get 4 over 5, a little higher up still. Let's kind of extrapolate out to 100. If I did 100, wouldn't I then get 99 over 100? Kind of gives us our ceiling. What are we converging upon here? 1. So this we would say converges to 1. All right. All of these are positive. Notice these are all above the x-axis. I guess you get some 0 values, but no negatives. Let's put it that way. When we go to number 4 now, you're going to see this little guy here. So we'll see a lot throughout this chapter. This little -1 to the n plus a 1 or -1 to the n. So when we now do this, now we want a first and a second quadrant. So when we go to graph that, have a first and second quadrant, and then we only need to go 1, -1. That's what we need on our vertical axis. This up a little for you. All right, so now be careful with these. If you let n be a 1, you would get a -1 to the power of 2. So that's going to turn that -1 positive. And then I would get 1 over 1. So the first value should be a positive 1. If you let your n be a 2, so we go to that second term, now I get a -1 to the third power. So that's going to remain negative. And I get 1/2. So I should be down here at a -1/2. So we were positive, now we're negative. If I go to 3, my exponent becomes an even exponent, so it's going to turn that -1 into a positive 1, and I would get 1 over 3, so now I'm at a positive 1/3. If I go to 4, odd power, so it's going to be a -1 still, 1/4, so now I'm at a -1/4 right here. Let's do one more with the 5. Makes this an even power, so positive 1 over 5. Now we're really tight to that. So notice how we're going positive, negative, positive, negative, positive, negative. That's what this little guy's going to do. It's going to alternate our sign from positives to negatives. And then as we see, positive, negative, positive, negative, positive, negative, are we converging or not to something? Yeah, we are still converging to something, correct? Even though we're doing it from a positive and a negative direction, aren't we eventually converging to the x-axis right here? So this, even though our signs change, we can still very much converge. And in this case, we are converging to 0. All right. 5, similar in that this should alternate. So this little prefix really is just telling us that we're going to bounce back. That's going to change positive, negative, positive, negative, positive, negative. So same thing, make this a positive 1, make this a -1, and then we're just going to go through 5, I think should be enough. Should change this here. No, we're good. So if I let, actually 1 is a 0, so that's pretty straightforward. Doesn't matter what sign you get. But if we then let the n be a 2, that gives us an odd exponent, so we're going to be negative. And then 2 would give us a 1 over 2, so it's going to be a -1/2. If I plug in a 3, makes an even exponent, so we're going to be positive, and then I'd get 2 on top, 3 on the bottom, so positive 2/3. If I throw in the 4, I get an odd exponent, so we'll be negative, and then I get 3 over 4, so now I'm at a -3/4. Actually, let's go to 6, just to make sure we can do this. 5 brings us back to positive, and then I get 4/5. 6 would bring us back to negative, and I would get 5/6, which is 0.83, so it should be a little further down than the previous one in the negative area. So now look at that guy. Think about what's going to be happening as we get further and further to infinity. Right? Ultimately, that's what we're kind of doing, going to infinity. What do we think? Converging or diverging?
Diverging.
Which one?
Diverging.
Why, Safian?
Because it's kind of like consistently going like outwards towards positive and negative and positive and negative. It never like really converges to 1 or -1.
Okay, good. That's a much better explanation. So you may think it converges because we kind of are, right? The top row of numbers is going to be converging to a positive 1. All these negative numbers are going to be converging to a -1. So that idea is correct. If that's kind of the thought in our head, we're going to go to 1 and -1. But overall, then, if we are asking, does this sequence of numbers approach a finite value? By saying that it actually approaches two of them means it really doesn't approach anything. So this is correct. And basically what he said is pretty much dead on. Since we're going to be bouncing back and forth long term, it's just going to be 1, -1, 1, -1, 1, -1. That would then mean that this function or this sequence diverges. Okay, good. All right, 6, similar to this one. This one's actually pretty quick. If you let n be a 1, I would just get a -1. So we'll be down here. If n is a 2, I get a +1. That's all I can ever get, right? Are -1s and +1s. So very much the same line of thinking that we just talked about here. Even though it's somewhat converging on both ends, the fact that it's going to two different values means that in general, then overall, this thing diverges. Okay? So we've seen this alternating one converged, this alternating one diverged, this alternating one diverges. All right? This also alternates. So let's see what this is going to do. I didn't leave us a whole lot of room to work with, it would appear. I never really think of these when I have the whole board to work with. So let's see if we can squeeze this in. So let's do 1, -1. We do it in arithmetic. Get all these. So 1, 2, 3, 4. Try to do this in red. All right, so let n be a 1. I would get a -1/2 to the first power, so that's a -1/2. If n is a 2, I'm going to get a +1/4. If n is a 3, I'm going to get a negative odd power, so it's going to be -1/8. And then if n is a 4, it's going to be positive, and then 1/16 is really tight. So this one is also alternating, positive, negative, positive, negative. Is this one converging? Yeah. So this would be a converges to a 0. So sometimes our alternating ones converge, like this one and this one, but we've also seen ones that will diverge. So we want to be able to identify, how can we do that without having to graph these things all the time? So if we look at this here, it says for numbers 1 through 7, think about our rules of infinity that we reviewed a little bit yesterday. Could these rules have been used to determine our convergence? So let's go back to, let's actually look at number 2 first, because I think it's easiest to understand what I'm referencing with these rules. If I actually ask you to find this limit, which is ultimately what this is asking in the infinite sequence, old rules wise, what would this limit give you? Where's your bigger degree at, top or bottom? Not quite. Just because there's no variable, the degrees are only for your variables. So since I don't have an n up here, that means the degree up here is actually a 0, and I have an n to the first down here. Yeah, so it's on the bottom. That limit is a 0. Isn't that what we got it to converge to? It was 0. This has a denominator of 1. We just don't have to show it. So now isn't the bigger degree on top? So didn't this have a limit of infinity, which would then make this diverge? If you look at number 3, here's the third combination of the rules that we talked about in the past. Aren't these degrees now the same? So shouldn't the limit converge to the coefficients of 1/1, which is what we got this to be? So now let's go to these alternating sequences. So here's the important thing to now understand. Look at the non-alternating part here. If I just asked you this, so pretend I can do this, erase it in a minute. Pretend that's not there. Don't cross yours out. But if I just ask you, what is the limit of 1/n? What would you say that limit is? 0. Even with it alternating, didn't we still converge to 0? Yes. When I come over to this one, if I get rid of the alternating part, and I just ask you this guy, what would this limit be? We just did it a minute ago. A 1. But this one diverged, correct? So think about how those differentiate and why we are getting these answers. If I'm going to be bouncing back and forth between positive and negative, the only way this could ever converge is if the non-alternating part right here goes to 0. That's it. Because if it's anything else, if this is going to behave more and more like a 1, then wouldn't the alternating part just bounces back and forth between 1, -1, 1, -1, 1, -1? So if we look at this next one, the general term is really just a 1, because here's our alternating part. So notice what we bounce back and forth between, -1, 1, -1, 1, because this would have been our limit if it wasn't alternating. This has to be a 0 in order for this thing to converge, and it's not. This one, what I would strongly recommend as we move throughout this chapter, when I give you ones that kind of combine the alternating idea as well as the general term, is to separate this. So this I will tell you to write down. So rewrite this as a -1 to the nth, and then do this as a 1/2 to the nth. Then it's easier to identify that this is alternating. And the only way we could possibly converge is if the non-alternating part goes to 0. I am then going to rewrite this one more time. Do we agree that 1 to the nth power is a 1? So my numerator is going to become a 1. And then in the denominator, I would get 2 to the nth. So what that really becomes is a 1 over 2 to the n. So think about yesterday when we were racing our functions towards infinity. Where is your faster growing function at, the top or the bottom? The bottom. So doesn't this limit have a 0 value? And the fact that it's alternating is why this guy, I guess I didn't write it yet, did I? Or did I erase it? I erased it. That's why this one would converge, because even though it's alternating, the non-alternating term here would have been going to 0. All right. Okay, we kind of understand that so far. All right, so now let's go to these, because what we don't want to have to do, the rest of this set of problems, the next 2 pages, is just answering that question, but we don't want to have to graph all of these. So if you look at number 6 and 7, I gave you kind of our line of thinking. If you go beyond number 7, you're not going to see the lower limit as n goes to infinity, but that's what we're really looking for as we move throughout. If this was our sequence of numbers, what would happen? So you're thinking a little bit, we don't want to have to graph all of these out. Think about what we talked about yesterday as we compared functions. Where is your faster growing function at, the top or the bottom? The bottom, right? And if the faster growing function is on the bottom, then this should be converging, because we should get a what for the limit? 0. So that should converge to 0. All right, if we look at number 7, a couple different variables involved. Bigger here. The n is the denominator of this fraction. So if we ignored this part right now, the x, wouldn't the 1 over n become a 0? Wouldn't that be its limit? And then regardless of what x is, don't we really just have x getting raised to what ultimately is going to become a power of 0? Which means overall, this would have to converge to what? 1. Anything to the power of 0 is going to be 1. 8 and 9, I think there's another one coming up, a radical. Here's what I would suggest, especially early as we get used to these. Rewrite this real quick. So this is an n squared. And instead of writing that to the nth root, rewrite that as a fractional power. So 1 over n. We could do it now, but as a general rule, to make sure we don't screw this up, let's go ahead, power to a power, remember you multiply. So let's write those exponents as 2 over n. So we have n to the 2 over n. I won't write this any longer, but we're still thinking this here. We're thinking what happens as n goes to infinity. It's an infinite sequence. So what are we going to approach, if anything? So as our n gets larger and larger and larger, wouldn't this be getting larger and larger and larger? But would it matter if your exponent is becoming a 0? No. That then overall tells us that we would still converge, since our exponent ultimately becomes a 0. Anything to the 0 power, even 1 billion, is going to be a 1. Okay, so that converges to 1. All right, so this one, same thing. Take your 3 to the n, raise it to the 1 over n. Pretty much the same thought process here. I would say that you may want to split these up if you have multiples. So 3 to the 1 over n, n to the 1 over n. But similar to those previous couple, this exponent's going to become a 0. This exponent's going to behave more and more like a 0. So don't we really have 1 times 1 overall? so that this is going to converge to 1. All right. All right, 10, 11, do those real quick. Those are actually old. We're just calling these sequences now, but our old infinity rules should work with these and make these very quick. All right, number 10. Let's see here. CC, where you at? Good. So this should converge to -1. The powers are the same, end of the first over end of the first, so we just look at their coefficients. -2 divided by -2 is -1. All right, and then 11. Let's see here. Ashley, what do you think? Good. So now we're to one that diverges because the degree on top of 2 is bigger than the degree on top of 0. So the limit is infinity. Now we're just writing that means it diverges. Okay. All right, next page. See what you think about 12. Take it up a notch with some of these on the next page. See what you think about 12. You can plot the points real quick. That plotting of the points that we did in those first 7 is strategically, I kind of do that. That's always something you can rely on a little bit if you need to. You don't have to. If we can look at this right away and kind of understand and have some number sense what's going to happen as we move along, we can just go right to that answer. All right. You got something, Stefan?
Yeah, I think it diverges.
I think it diverges also. Why does it diverge?
It's the same graph as before, so it's shifted up 1.
Oh, that's clever. I like that. So what Stefan said was, we already did this one, right? The -1 to the nth. And we said that diverges. And what he then recalled is that all we really did by adding a 1 is shifted it up 1. So that's going to make it diverge. I was actually going to show the graph, but that'll actually kind of prove out, instead of -1 to 1, well, we're going to bounce back and forth between it. Since it is shifted up 1, only thing we're ever going to spit out here is a 0 and a 2. 0 and a 2, that's it. So it really is that -1 to 1 getting shifted up 1. Clever, Stefan, I like that. That diverges. All right, 13 now. Strongly recommend, as you see these, separate the alternating parts from the general term. So by that, I mean, let's pull out the -1 to the n plus 1. Because once we identify that that's going to be bouncing forth between positive, negative, positive, negative, positive, negative, the only way that this could converge, once we know that we're alternating, which is what this is telling us, is that this guy here must go to what? Gotta go to 0. So does this limit for just this part, does that actually then go to 0? Yes. So because of that, this will converge, and it's going to converge to 0. If we were to graph it, it's one of the ones that, even though we're bouncing back and forth, we are eventually going to be approaching that x-axis. We're going to converge to 0. Okay? Write down what you think 14. This is not one. It's a common little question here, but first time you will have seen it. So what happens to this as n goes to infinity? You can kind of think yesterday's notes, where's the faster growing function at? It's that idea. Geez, let's crap out here. All right, what do we think, Zach? Converge, diverge? If it does converge, what do we think? Brave. Anybody? What do you think? Well,
I think it converges to 0.
I think it converges to 0 also, Mo. Good. This should converge, Mo says, to 0. He is correct. Why did you think that, Mo? What was your thought?
I think I recall that sign is growth is slower than just variable.
All right. So
The bottom is going to grow faster than the top.
All right. So what he's saying is the bottom grows faster than the numerator. That this is going to get bigger and bigger and bigger. It's going to become infinity, and it's going to grow faster than this. That is, I'm going to say, like 85% correct. Just because, think about the sine function. What does the sine function look like? Doesn't the sine function just do this over and over and over and over again? So does the sine function really even grow at all? No, it's locked in between 1 and a -1. So if this is always in between a -1 and 1, and this is going to become 2 million, 3 million, 4 million, and 5 million, doesn't this then overall just continue to get smaller and smaller and smaller? All right. So that should converge, and that's why that's going to converge to 0. Okay, if we graph this as we go further right and left, you're still going to kind of swing up, like I said, and make it big enough, but you're going to get tighter and tighter and tighter to the x-axis as we get further and further to the right. Okay, good. All right, next one. See what you think for that one. All right, Carter, what do you think, Carter?
I said that it converges to 1.
You're really loud, Carter. I'm going to turn down a little bit. All right, what was your thinking there, Carter?
Because both of them have a power of 1, so that equals 1, but then the square root of 1 is just 1.
You're really, really warm. So these both have powers of 1, he said. So that is correct. So if I got rid of the radical, let's pretend that's not there. With these being a power of 1, we just look at their coefficients, right, Carter? What are their coefficients, though, Carter?
1 over 1. Oh, wait, coefficients. 2 over 1.
All right. So the inside would behave more and more like a 2 over a 1, right? As the n becomes infinity. So that's going to give us this, but the square root of all of that is there. So this should ultimately converge to the root 2. All right. Good. 16, I think we can do. Try 16. As n gets bigger and bigger and bigger, what's going to happen overall to that value? All right, what do we think for this one? Nick?
I think it converges to 1.
You guys are doing a lot of good thinking today. I agree. That should converge to a 1. Why, Nick?
Because as you go to infinity, I would choose 1 over n. 1 over n is just going to tend to 0. So you're just going to be left with pi over 2, which is 1.
Perfect. I don't know if you could hear that at home, but he explained it pretty much perfectly here, where he looked at the 1 over the n, and as our n's go to infinity, he said this is just going to tend towards a 0. It's basically going to become inconsequential. It's going to become pretty much nothing. So all we really end up with is the sine of pi over 2. Sine of pi over 2 then is a 1. So we're going to get closer and closer to the value of 1. 17, be careful of. I won't ask you to do this one. A little guidance here. We don't want, it's kind of like when we did the integrals with these, we don't want to really handle these until these are completely simplified. A simplified natural log is 1 natural log, ideally with a coefficient of 1. So the fact that we're subtracting natural logs, remember how that means we could actually divide these and create 1 natural log? Once we do that, then that should be obvious. So now do this. Now I would tell you that you should be able to do this one without a problem. As n's get bigger and bigger and bigger, what's going to happen then overall? And we do have to remember something somewhat old. And this should converge to what? Well,
0.
Good. Should converge to 0 because the inside, Nick, is going to become a what?
Oh,
Good. The inside is going to start to become a 1. So if we got rid of this, n over n plus 1, they have the same exponent. So you look at their coefficients, that's a 1. But the fact that we then are ultimately going to be taking the natural log of a 1, that's the value of 0. All right. 18, a little trickier. Another one that's we probably want to talk about a little bit. We can't really rely on which function grows the fastest because these are both incredibly slow. Natural logs grow really, really slowly. So this is where when you've got to answer a question like this and we really don't know which one of these grows the fastest, so as n goes to infinity, these both do legitimately go to infinity. They just do it really, really slowly. So because of that, this is one that we may want to do L'Hopital's rule with, where let's take our derivatives and then try to evaluate the limit. So take the derivative of the numerator, so 1 over n. Take the derivative of your denominator, 1 over 2 to the 2n times 2. And I guess I don't want to use that. But let's simplify this now. So this is 1 over n over the 2's are going to cancel. I get another 1 over n. Notice how then those completely cancel, or at least reduce. They don't necessarily cancel, but they reduce down to be a 1. So if I now ask you what is the limit as n goes to infinity, the limit of any constant is that constant. So this would have to converge to that limit of 1. Now, 19 is a big one. 19, 20, I think 21 too, if I remember correctly. So this is an important one because this is tricky business here. Let me actually add a, let's do it off to the side here. So we'll call this number 20b, so right after number 20. And tell me what you think is going to happen to this. 1 plus 1 over n to the nth. So as your n gets bigger and bigger and bigger, what is going to overall happen to this value? So I'm afraid to call on anybody because this is a sucker question here. Because it's a trick question. Count. Okay. You're going to say 1?
Yeah.
We're going to say a lot of 1s. Okay, intuitively, you're going to think it is a 1. Now, Andrew says he doesn't think it is a 1. So before we let Andrew say this, see if he's correct. This should look familiar to us. We've talked about it a little bit in the past. One day during our notes, you would have seen this in the past before. We'll see if Andrew can guide us a little bit. As n goes to infinity, what did we say that this was, Andrew? It is. That converges to e. Very, very much counterintuitive. I would completely understand why you would say 1, right? Because doesn't the inside of this become a 1 or a 0? So doesn't this really look like we just have a 1 to the nth power and then 1 to the nth? Any power is still going to give you a 1. Yeah. So that is really, really tricky. So if you got a 1, pretty much everybody else probably got the 1 as well. But in this case, this is very much counterintuitive. That's where E comes from. That's why people in the past actually assigned a value to this, because it was very weird that this would happen. But just to show it so you don't think we're making this up, if I went ahead and graphed this, what should happen if it's a 1 is we would get towards the line y equals a 1. If it's E, we're going to approach 2.7. So if we now hit graph, notice how we go further and further right. Remember how E was 2.7-ish? Notice how this is leveling off towards 2.7. All right. You want to commit that to memory, because if you rely on kind of just, what we've been doing, you're going to absolutely think this is a 1. Okay. So go back to now number 19, because now we can talk about 19 a little bit better. That should look very, very similar to the one that we just did. Instead of a 1 right here, I have an X. What that means is this would converge to e to the x. So whatever the numerator of this guy is, in this case it's an x, that's the exponent for your e. The one that we added, the exponent was a 1 here. Okay. So that's why the exponent was a 1 over here. Number 20, you want to recognize that we can simplify this. So if I did n over n minus 2 over n, and then to the nth power, that should look like the 20b that I gave you, and then number 19. You could even think of this as a plus a negative 2, maybe. That might be more obvious. So when we see this combination, 1 plus a constant over n, or anything over n, raised to the nth power, this is going to converge. And what it is now going to converge to is e, and then whatever this numerator is the exponent. So e to the negative 2. All right. All right, real quick, 21. I want you to see these because I want this recorded for first or 7th period to watch in its entirety. If we simplify that, we get another one. This is going to converge to e to the what now? E to the 3rd. If you want to throw them on your calculator at time, usually if it has some time, I show that we're not just making this up. That should be e cubed. All right, 22 you can do. That's going to be, it's going to converge to 1 because you get 8 to the 0. 23 we actually already did. All right, jump down to 24. Let's not make this harder than it needs to be. Change that negative 4 to a positive 4 so that we don't have to worry about the alternating thing. Did these yesterday. Remember how we had the little hierarchy? Natural logs, they're slow. They try really hard, but they're not very fast. And then these all grow faster. Eventually, e to the x beats all of these guys, but like a 4 to the x beats that, a 10 to the x beats all. These are our fastest. So if I now look at 4 to the n, and then n factorial. Do you remember what a factorial is? All right, so I give you 10 factorials, 10, 9, 8, 7, 6, 5, 4, all multiplied together. So 4 to the n, exponential functions grow very, 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 very fast. And if I had time, I'd show this on the calculator. But exponential functions meet their match with our good old-fashioned factorial. It's crazy stuff here. So this is going to converge to 0. Maybe no, we have a test tomorrow. I want to revisit this because even here, the two exponential functions, they get mad and they team up on the factorial, right? They team up 2 to the n times 3 to the n because they're mad that they lost. This would still go to infinity because the n factorial is going to grow faster than this. We'll put it in the calculator. I'll show you on the table how this works. This is what I tried to show you yesterday. One starts out faster, but the other one eventually catches up. Okay? All right, if you have any questions, I'll be available tomorrow at 9:30. I'll hop onto the class link. So if there's any last questions on the test, let me know. And then, yeah, good luck. We'll see you tomorrow. Thanks, Aaron. You too.